Hello and welcome back to the video lecture series for ECE-340. I'm your instructor, Dr. Bradley Duncan. Today we're going to be talking about everybody's favorite topic, conditional probability. In particular, we're going to be looking at conditional probability density functions and cumulative distribution functions, how we might calculate them, how we might work with them. So to begin, let's go back and review just a bit. Let's remember the fundamental relationship for conditional probability. Remember, probability that event A occurs and event B occurs equals the probability that event A occurs if event B occurs times the probability event B actually occurs. Okay? That is an axiomatic statement, meaning that I can't prove that to you from more fundamental relationships. It's an always and everywhere true relationship. It's something I ask you to repeat to yourself over and over and over again until you convince yourself that it's actually true. So in shorthand notation, this is the probability that A occurs and B occurs. That comma there always means a conjunction. And probability of A occurring and B occurring equals the probability that A occurs if B occurs times the probability that event B actually occurs. And that vertical bar is my conditional, if. All right. Simplifying even further, I can say probability of A if B equals the probability of A and B divided by probability of B. All right, that's one of our fundamental relationships for conditional probability. All right. Now, let's talk about a couple of interesting events. I'm going to let A equal x less than or equal to some level little x. And I'm going to define another event. This time I'm going to call it B, or excuse me, I'm going to call it M. M is, this is going to look a bit mysterious when I first write it down. Let me write it down, then I'll explain what I mean. Y is an element of some set R sub y. All right. This is just a set or a collection of outcomes, and it's an event. All right, it's just an event with multiple outcomes for y. I'm trying to write this, this is going to be my conditional event shortly. All right, my conditional event is that y takes on one or more values in some arbitrarily defined set, capital R sub y. R sub y is just an event with multiple outcomes. All right, that's all it is. All right, the probability of A and M occurring equals the probability of A if M occurs times the probability that M actually occurs. A is x less than or equal to some value, and this equals probability x less than or equal to x if m times probability of m. Maybe I should use capital M's. I started with capital M's. Let's use capital M's. All right. Rearrange this a bit, and I get the probability x less than or equal to some unspecified level little x if m. And that now I can recognize as a conditional CDF. Anytime I look at a random variable less than or equal to some unspecified point, I'm talking about a cumulative distribution function. And that can be written as the probability of x less than or equal to little x and event m occurring divided by the probability of event m occurring. All right? This is an important relationship. This is my conditional cumulative distribution function. All right? It's the CDF for x. It's the CDF for x, rather. Let me write that again. CDF for x conditioned on m occurring. What's the probability that random variable x is less than some specified level little x, given that we know that event m occurred? That's what that means. That's the conditional CDF. Talk about properties of the conditional CDF. They're very similar to non-conditional CDFs. 1. Conditional CDFs always lie between 0 and 1. Okay? Conditional CDFs are always less than or equal to 1. Or, excuse me, fall within the range 0 to 1. Well, I guess they are less than or equal to 1. They fall more specifically within the range 0 to 1. Second property is the cumulative distribution function evaluated at minus infinity is 0, and the cumulative distribution function evaluated at plus infinity equals 1. Third property, this thing is always non-decreasing. It's always a non-decreasing function of x. It's continuous from the right. That's really more applicable if we were talking about discrete conditional CDFs. We're not going to go there. And then my last property, probability of x falling within a certain range. All right, you just subtract, if you want to find the probability that x falls within the range x1 to x2, given that event m occurs, well, that's, you just subtract the conditional cumulative distribution functions for x evaluated at x2 and x1. All right, basically the same as for non-conditional CDFs. Okay? All right. What about the conditional probability density function? What about a conditional probability density function? Well, just like with non-conditional PDFs, conditional PDFs, the conditional PDF is found by taking the first derivative of my conditional CDF. Same as before. All right? I find my conditional PDF by taking the first derivative of my conditional CDF. Properties. Basically the same as for non-conditional PDFs. Conditional PDFs are always positive. It's always positive. Another property. Its area is 1. Area is 1. I can find the conditional cumulative distribution function by taking the indefinite integral of the conditional PDF. All right, and my fourth property. If I want to find the probability that x falls within a certain range between x1 and x2, given that event m has occurred, well, I just integrate my PDF from over the limits. x1, x2, just like that. All right. Once again, those properties ought to look really very familiar to you. They are essentially the same as what we've seen in the past for non-conditional PDFs. Okay? All right. Let's look at a special case. Kind of an important, pretty useful special case. What I'm going to do is I'm going to assume that y equals x. In other words, I'm only talking about one random variable, x. And I'm going to let my conditional event, m, be that x is less than or equal to not a variable level, but a specific value. Random variable x now is a specific value, little m. Okay? So this is my sort of a general scenario. That's a specific value. M is a specific value. This would be my non-conditional PDF. And I've just arbitrarily drawn it as a Gaussian here just because it's easy to do so. What I would like to find is, for this special case, I'd like to find the conditional cumulative distribution functions and cumulative the conditional cumulative distribution function and the conditional probability density function. Let's find the conditional CDF first. From the couple of slides back, we have this. This is my conditional event M here, right, divided by my conditional event, probability of my conditional event, there. Okay? All right. Now, let's make some observations here. Remember, my comma means an and. My comma here means an and. That's important. If my variable little x is greater than or equal to m, then the probability, I'm looking at the numerator, if the probability that x is less than x and at the same time x is less than or equal to m, well, that's the probability that x is less than or equal to m. All right? If x is somewhere up in this range, let me pull out a colored pen. If x is somewhere up in this range, greater than m, and at the same time I know that my random variable is less than m, well, the probability that x is less than little x and x is less than m is just the probability that x is less than m. So, plugging that back up into my numerator, I get that. I get exactly 1. All right? And this is for the case when x is greater than m. All right? What about if x is less than m? Still dealing with my special case here now. If x is less than m, then the probability that x is less than or equal to x and x is less than or equal to m is simply the probability that x is less than or equal to x. I'm saying up front, x is less than little m, and at the same time I know x is less than m, so the probability that x is less than some value smaller than m, given that x is already less than m, that's just probability that x is less than x. Capital X, random variable x is less than or equal to x. And so, we get that. All right, my cumulative distribution function for x, conditioned on m in this special case, is the marginal cumulative distribution function for x divided by the marginal cumulative distribution for x evaluated at the specific point little m. All right, in summary, for this special case, All right. For my special case that we're talking about now, my conditional cumulative distribution function looks like that. Now, next thing we'll notice is that I'll notice that my cumulative distribution function for x evaluated at little m is less than 1. All right? So, for the region x less than m, my conditional CDF is greater than my non-conditional CDF. All right? So notice that remember, cumulative distribution functions are always between 0 and 1. Unless m equals plus infinity, the cumulative distribution function evaluated at little m is something less than 1. Divide by something less than 1, I get a number bigger than 1. So my conditional cumulative distribution function in the range x less than m is greater than the non-conditional CDF. But my conditional CDF has the same shape as the non-conditional CDF. All right? So let's sketch that out just a bit. That's why I wanted to draw a picture down here in the lower right-hand corner, so I've left myself a lot of room. All right, let's assume that this solid black curve is my non-conditional CDF. And let's pick a point right here and call this value m. All right, so for this special case, my cumulative distribution function for x greater than or equal to m is exactly 1. Always. And below m, my conditional cumulative distribution function is greater than the non-conditional cumulative distribution function, but follows the exact same shape. Let's see if I can trace this out. All right. It's supposed to be the same shape. I apologize, I'm not the greatest artist, but the red curve below m is supposed to be exactly the same shape as the black curve below m. This red curve then is my conditional cumulative distribution function for this special case. All right. What about, now that we know, let's look at the conditional CDF, PDF, conditional probability density function. Let me just begin by reminding ourselves what the conditional CDF looks like. All right, that's my conditional CDF. That's my conditional CDF. Let's find the conditional PDF. It's just the first derivative of the conditional, the conditional PDF is just the first derivative of the conditional CDF. and that is going to be okay, for the region little x less than m, my first derivative is only with respect to the non-conditional PDF or CDF for x, and I pull this thing. This is a constant. The non-conditional cumulative distribution function for x evaluated at m just comes outside the derivative. All right, and of course, the derivative of 1 is 0 if x is greater than or equal to m. All right. So in summary, my conditional PDF equals right? And once again, keeping in mind that my non-conditional cumulative distribution function for x evaluated at m is less than 1. So my conditional PDF is greater than the non-conditional PDF, but follows the same shape. And of course, this is in the region where x is less than m. All right, so let's sketch that out a bit. If this black curve happens to be my non-conditional PDF, all right, and let's say this is value little m. Above little m, my probability density function, that's supposed to be 0. My probability density function is exactly 0. And above m, or excuse me, below m, my probability density function follows exactly the same shape, but is a little bit larger. Okay? This is my conditional PDF. All right, and way down here in the corner, that's 0. Okay. A couple other things. I can do conditional expectation. And what I'm getting ready to write down is true in general and not just applicable to the special case I did just a couple of minutes ago. All right. In particular, I can find the conditional mean. This is integral from minus infinity to plus infinity x. That's a conditional mean. That's the mean value of x given that event m occurs. I can also do the mean of functions of x. Okay, that is the mean value of a function of x given that event M has occurred. All right. Let's do some examples. All right. This first example relates back directly to the special case that we talked about just a few minutes ago. And this is going to be my example. I'm gonna shoot a bunch of arrows at a circular target. I'm going to shoot a bunch of arrows at a circular target. The radial distance from the center of the target, the radial distance of the impact sites relative to the center of the target, the radial location of impact sites relative to the center of the target is a Rayleigh random variable. All right, we're going to make that assumption anyhow. And my Rayleigh probability density function looks like this. And for this particular problem, I'm going to assume that A equals 4. All right, and I guess I should define this. Capital R is my random variable for the location of impact sites relative to the center of the target. So capital R is my random variable. All right, this is a non-conditional PDF. All right, this is a PDF which describes the impact sites for every arrow I shoot, whether or not they actually end up hitting the target. We'll talk about the target in just a minute. This is a non-conditional PDF. Applies to all arrows shot whether or not they hit the target. Okay. The non-conditional mean. The non-conditional mean is A times the square root of pi over 2. We've seen this before early on. And in our case, A is 4. And that turns out to be, well, we'll say A is 4 inches. So the non-conditional mean radius of impact sites for all the arrows that are fired at the target, whether or not they hit the target, is 5.013 inches. All right, this is the non-conditional mean. All right, this is the non-conditional mean. This is the mean radius of impact sights for all arrows I might shoot at my target, whether or not they actually hit the target. Okay? So, now let's assume that my target is 12 inches in diameter. Okay? Radius of 6 inches. Okay? And what I want to find is the mean distance from the center of the target for all those arrows that actually hit the target. All right? For those arrows that hit the target, what is their mean radius So this is the question we want to answer. For those arrows that actually hit the target, what's their mean impact radius from the center of the target? Okay, this will be a conditional mean. This is a conditional mean. A conditional mean. All right, so from our work a couple of slides back, my conditional probability density function is Alright, that's what my conditional probability density function looks like. Well, I need to calculate the cumulative distribution function evaluated at 6. From our previous work, a few videos ago, my cumulative distribution function for the Rayleigh random variable, this is non-conditional cumulative distribution function, equals 1 minus exp negative r squared over 2a squared. And there's a step function in there. So you can plug in 6. A of course equals 4. You plug that in and you'll find that the result is 0.67534. Okay? In our case, A equals 4. Alrighty? Alright. So, let's find the conditional mean. This is an integral from 0 to 6. Notice that my lower limit has to be set equal to 0 due to the step function in the Rayleigh probability density function. There is no value for little r less than or equal to 0. This is r That's the interval I need. All right. And this equals integral from 0 to 6 r squared 1 over a squared equals that. And put in all the values that I know. I know a equals 4, and I know what the non-conditional cumulative distribution function for r is evaluated at 6 from the previous slide. I get 10.806 in the denominator. Integral from 0 to 6 r squared e to the negative r squared over 32 dr. Now, I came to an integral that I couldn't integrate by hand, and I didn't readily find an applicable entry in any of my integral tables. So I turned on MATLAB and I integrated this integral numerically. If you don't know how to do that, let me know. I'll coach you through it. It's really very simple. By the magic of MATLAB, I performed that integral, divided by 10.806, and the result was 3.5476 inches. Okay, and you'll notice that that is less than the conditional or the non-conditional mean radius of impact sites for all the arrows, whether or not they hit the target. For those that hit the target, the mean radius of impact sites is somewhat smaller. We ought to expect that. The mean radius, the non-conditional mean radius for impact sites was about 5 inches. But that included all the ones that hit the target and didn't hit the target. Once we include only those arrows that actually hit the target, well, the mean radius is somewhat smaller. Okay, let's do another example. This example does not leverage our special case that we examined earlier, so we've got to do a few extra steps. So this example has to do with a company that makes meter sticks. Somebody's got to do it. There's a company that makes meter sticks. The non-conditional PDF The non-conditional PDF describing the length of all the meter sticks that come off the production line by some event was determined to be Gaussian. Not surprisingly, the mean length of my meter sticks is 1 meter or 1,000 millimeters, and we will assume that for this example that the standard deviation of my meter sticks coming off this assembly line is 2 millimeters. All right, and all my meter sticks are inspected after coming off the line in some quality control step, and they're rejected if they are 1 millimeter too long or too short. Okay? That means that the meter sticks are going to assume to be appropriate quality if they lie between 999 millimeters and 1001 millimeters. All right. So what I want to do is I want to find the PDF for the meter sticks after throwing away those that are either too long or too short. All right, so I want to find the conditional PDF for the meter sticks after throwing away those that are either too long or too short. So my conditional, well, let's do this. We'll say that x equals, my random variable x is my meter stick lengths my probability density function, my non-conditional probability density function is 1 over sigma square root of 2 pi e to the minus x minus m squared over 2 sigma squared. And in our case, this would be 1 over square root of 8 pi e to the negative x minus 1000 squared over 8. And my conditional event is m is 999 less than x less than, oops, too many zeros. That's my conditional event. All right. Now remember, my special case several slides ago was that x fell less than some value little m. Now I'm saying that x falls within a range of values. Okay? All right, well, one interesting question we might ask right off the bat is, what's the probability that my sticks are of an appropriate length? Let's do that first. We'll get back to doing the PDF shortly. We'll need this anyhow. Probably that my sticks are an acceptable length. Well, let's just kind of reason that out by drawing a picture. My non-conditional PDF looks something like this. All right. Right there is my mean, m. And let's put a point here and call that x naught. Remember, that area, and oh, by the way, I can draw this in and show that my Gaussian has a standard deviation of sigma. Way down here is 0. All right, so the area under that upper tail is defined by my Q function. This is Q of x naught minus m over sigma. All right? If that range right there is delta, then if I have another point right here, which is, let's call that x1, and we'll say that x1 equals m minus delta, that area right there is also, by symmetry, q of x naught minus m over sigma. By symmetry. Okay? All right. So let's let x naught equal 1001 millimeters. Let's let m equal 1000 millimeters. And x1 will be 999 millimeters. Then and remember this also, this is a proper probability density function. The total area is 1. Total area under that thing is 1. All right. So the probability of m in this case, which is the probability of 999 less than length of my meter stick, this equals 100% of my area minus 2 times the area of my upper tail. All right. The total area under my Gaussian curve is 1 because it's a proper probability density function. I want to find the probability of lying inside of this region here that I'm drawing in as red. That's clearly got to be 100% minus 2 times the upper tail. The area of the upper tail is q of x naught minus m over sigma. So this is going to be 1 minus 2 q of, keep putting in too many zeros, 1001 minus 1000 divided by 2. This is 1 minus 2 q function evaluated at a half. You can look that up in tables, or you can use the q function MATLAB code that I sent you earlier. You can calculate that on out. And this is 0.3829 or 38.29%. So interestingly enough, that means that only slightly over 38% of the meter sticks for this particular production line are considered to be acceptable, meaning that they lie between a length of 999 millimeters up to 1001 millimeters. It's a pretty wasteful production line. In this particular case, a standard deviation of 2 millimeters is pretty enormous. Plant manager might want to see if he can tighten up quality control just a bit. All right. We're going to need this in just a minute. Remember that we are trying to find the probability density function for the meter sticks which remain after we throw away those that are either too long or too short. So, we're going to do this by finding the conditional cumulative distribution function first, and then take the first derivative. Okay? That's what we're going to do. And right? This can then be written, you'll notice that the denominator is probability of my conditional event, which we calculated on the previous slide. So this is 1 over okay? That's that. All right. All right. So now let me just write down my result here, and I will then attempt to reason it out. So this is the probability that x is less than some level little x, and at the same time, remember that comma always means an and. So my result is the following. Let me just write this down for you. Maybe I'll just go to another page because I'm going to need a little bit of room. Again, let me just write it down. Okay? That is my conditional cumulative distribution function result. Let me reason that out for you by drawing a little bit of a picture. Okay? All right. Now, my conditional event, let's write down what my conditional event here. My conditional event is that my meter stick lengths are between 999 and 1001 millimeters. So if I know, that's what this if bar means, I know that my meter stick length is between 999 and 1001, then if x up here is greater than 1001, I know it's 100% likely to be less than that value. If little x is greater than 1001 millimeters, the conditional cumulative distribution function has to be exactly 1 because I know it lies between 999 and 1001. Likewise, if I know it lies between 999 and 1001, the probability that it's less than 999 has to be exactly 0. Has to be exactly less than 0. All right, what about the intermediate range? The intermediate range, let's call this point here x naught. And this hatched out area here, that hatched out area there is the cumulative distribution function for x evaluated at x naught, given that I know I'm within the desired range. All right? The region between that point and that point is my conditional event. I know that I'm in that range. I know with 100% certainty that I'm within that range. The conditional cumulative distribution function for x evaluated at x naught, assuming that x naught is within the desired range, this equals what? Equals the cumulative distribution function at x evaluated at x naught minus, we throw away all that stuff less than 999 millimeters. That's where that goes. Okay? That's where that comes from. So if I know that I'm in this particular range, between 999 and 1001 millimeters, I end up with the cumulative distribution function evaluated at x minus the cumulative distribution function evaluated at 999. I also need to multiply times this 2.615 value because of what we had on my previous page. 1 over 0.3829 equals my 2.611 value. Okay? That's what that is. All right. Next question is, what is my cumulative distribution function evaluated at 999? That's just 1 minus q of negative 0.5, and by symmetry that is q of 0.5, and that is 0.3085. Okay? All right. A couple more steps here and we'll have the conditional cumulative distribution function. Recall that the non-conditional cumulative distribution function for a Gaussian random variable is 1 minus q of x minus m over sigma. All right. So my conditional cumulative distribution function is then written as 1 for x greater than 1001, 2.6115 times 0.6915 minus q of x minus m over sigma. And by the way, that value is 1 minus my conditional cumulative distribution function evaluated at 999. And then it's 0 in this range. Okay? It's there. That's my conditional cumulative distribution function. Okay, that's my conditional cumulative distribution function. To find my, remember I'm still trying to find my conditional PDF. I'm going to do that by taking the derivative of this function, all right, my blue starred function. I'm going to find the conditional PDF by taking the derivative of my conditional CDF in this form, because I know the derivative of that is just a non-conditional PDF. Okay? From my starred equation, a couple of pages back from that equation, we find my conditional probability density function, which is the first derivative of my conditional cumulative distribution function. That's just very simply 2.6115 times my non-conditional PDF, but it's valid only in this range. Okay? The derivative of 1 in the conditional CDF is exactly 0. The derivative of 0 in the conditional CDF is exactly 0. If we go all the way back to this guy, the derivative of 1 is 0. The derivative of 0 is 0. The derivative of that thing is 0. So what I end up with is, in the range 999 to 1001, I have 2.6115 times the derivative of my non-conditional CDF. Gets me to that result right there. Gets me to this result right there. All right, that's my result. That's the answer for part A. And yes, there is a part B. Part B. All right, this is going to be I want to find the probability that the meter stick lengths what's the probability that the meter sticks lengths are within plus or minus 1/2 millimeter after throwing all those away that were either too long or too short. All right, so remember, we throw away all the meter sticks that are either 1 millimeter too long or too short. After we throw away those that are either too long or too short, what's the likelihood that those which remain are within 1/2 millimeter of the appropriate length? All right? I'm asking myself the following question. Well, let me move. I need a little bit of room. I'm going to move to my next page. I'm asking myself this question. What's the probability I want to find the probability that my meter stick length is between 999.5 millimeters and 1,000.5 millimeters, given that I know that they lie between 999 and 1,001 millimeters. This equals integral from 999.5 to 1,000.5 of 2.6115 times my non-conditional PDF. All right. This equals 2.6115. Alright, plugging in my non-conditional PDF, I get there. Alright, now what I'm going to do is I'm going to make a change of variables. I'm going to let u equals x minus m over sigma and du equal dx over sigma. After change of variables, I get 2.6115. Integral from negative 0.25 to 0.25. 1 over square root of 2 pi e to the minus u squared over 2 du. You'll notice now that my integrand, that's a zero mean. Unit variance Gaussian. Alright. So I can use the Q function to evaluate it. And specifically this is 2.6115 times 1 minus 2q of 0.25, exploiting symmetry. You can use the Q function, MATLAB formula or MATLAB M file that I gave you earlier if you wish, or you can look up the results in the tables. After working this all out, I get 2.6115 times 1 minus 2, 0.4013, and that is 0.5155 or 51.55%. Okay, so what that says is after I throw away all of the meter sticks that are either too long or too short, a little under 52% of them are within a half a millimeter of the correct length. I really think the plant manager ought to tighten up quality control. One last question might be, what is the probability that what's the probability that meter sticks are within plus or minus half a millimeter of 1 meter before throwing any of them away? In other words, I'm asking myself this: what's that? That is a non-conditional probability. You'll notice there is no vertical bar and an M in there. This equals I'll let you do this. It's the same steps I used on the previous page, and I get 1 minus 2q of 0.25, and that is 0.1974 or 19.74%. You'll notice there's no 2.6115 multiplying the result at that point. All right. So before I throw away any meter sticks that are either too long or too short, something less than 20% of them are within a half a millimeter of 1 meter. After I throw away the ones that are either too long or too short by 1 millimeter, those that remain, about 55% of those are within a half a millimeter of the correct length. All right. Well, I know that was really long, and I apologize. I had a couple of good examples I needed to go through with you. As usual, if you have any questions, please do contact me at your earliest convenience, and I'll answer them as thoroughly as I can. Have yourself a nice day. Bye-bye.